Everyone. Welcome and thank you for tuning in to our final session for today, which is the fundamentals of electrical troubleshooting session. Before we get started, I would like to take a moment to thank our sponsors, Rainbird, Hunter, Ewing, and Brightview for helping make this event possible. Some housekeeping notes before we get started. I have muted everyone by default so we won't be distracted by latecomers. Please keep your microphone muted throughout the presentation unless you have any questions. During the presentation, if you do have questions, you can ask verbally or use the chat box if you prefer. I will be monitoring the chat box throughout the entire presentation, so your questions that are posted there will be relayed to our speaker. Without further ado, I would like to welcome Brad Jakubowski.
Cool. Thanks, Nicole. And thank you, everybody, for being here today. It's just great to have all of you here. And I guess we'll just kind of get started with some of those things. My goal for today is to, I guess, share with you some of the things that I've been doing as far as teaching electrical troubleshooting. And hopefully there'll be some skills that you guys will be able to pick up then from some of the things that I've been able to develop. And we'll just kind of we'll be able to have a little bit of an open forum with this. I do have a PowerPoint that we'll be able to follow, and I'll take you through, I guess, some of the construction process that I had with the little test stations that hopefully each one of you received. That's one of the first things that we'll do. So let's go ahead. Let me go ahead and start. I'll share my screen with you. And let's see, we will go to, let's go here. All right. Okay, so hopefully did everybody receive, I guess everybody that had registered, did everybody receive your test station okay? Hopefully it did. Hopefully you did. Let me know, I guess the biggest challenge was some of your corners might have gotten dinged a little bit with the foam board, or hopefully all of the wire nuts stayed in place. If not, they should have been fairly, I suppose, simple to be able to do that. So that's kind of what we'll talk about first. Was this is what it, at least this is what it should look like, something like this. And so you should have received a digital multimeter from Harbor Freight, and also this little test station that I was able to construct. Many of you may have already have something like this, but this was something that I started using a couple of years ago, working with the students, because I didn't have enough controllers for everybody. So then I wanted them to be able to have an opportunity to get their hands on with something like this. And so they could do some wiring. And then once COVID hit, then I was also able then to build these and ship them out to the students. And so hopefully we'll kind of go through some of these things. And so hopefully everybody got all of these parts and pieces okay. And then we will go from here. These are my goals for everybody today. And our goals then, the first one, to provide a potential relatively new method for teaching troubleshooting. I'm hoping that maybe this will provide you maybe some new ideas or something that you might be able to work with, some new concepts. Also, I'd like to receive your input as we go through this, and feel free to, you can take these things apart once we're done today, or as we're going through the presentation today, or kind of our meeting today. If there's some other things that you kind of think, aha, I think this might be a better way to kind of work with this, or something like that, I would love to hear it, and then we can kind of share it with the group. And then also, hopefully, if I don't talk too long today, at the end or near the end, I'd like to have us as a group develop, as we go through this process, and some of the things that I'm going to be working with today then would be, let's at least develop like 5 questions or ideas to task our students with. So as you're working with these, you're thinking, okay, what can I do? Okay, this is something that I can do on an exam, or this is something I can do for a project, or for a homework assignment, or something in class, or whatever it might be. And this would actually be something that you could actually send home with them. They could actually build it, and either they have to work with somebody else, obviously, or it's kind of would be somewhat difficult to, I suppose, I don't know, cheat on or whatever, but it would be something that they could also do that way as well. So we'll see what we can come up with. All right, so I'm going to, there we go. So I'm going to kind of go through some learning moments, things that maybe that we can kind of either learn from or some teaching moments. And so the first one is kind of, this is something for us, is the materials that I used. I did share in Dropbox a Word doc with the materials that I did use to build these. And I can then supply, I just kind of hand built a manifold and then took a photograph of those, of the manifold of the different valves, and then was able to then print those off. And that would be one of the things that I used. Also then 18 gauge sprinkler wire that we have. This was 18.7 wire that I used on those. And if you wanted to use different colors, you would be welcome to do so. And then from there, I also have, it's kind of hard to see, is I did use 1/8 inch 3-to-1 shrink heat shrink tubing for this. I've used 2-to-1 shrink heat shrink tubing in the past, but it just didn't quite hold on to the wires and the resistors quite tight enough. And then also I got some 16 gauge speaker wire that would simulate the wires coming in out of the solenoids. And then these little 6-pin barrier strips. In the past, I've used 8, but our access, we could use this. Fortunately for our project, the 6-pin barrier strips worked well. These are Molex, and we got these through Allied Electronics. And normally, fortunately, these aren't too crazy expensive. Oops, excuse me. These here, they might cost you about $3 a piece, 2 to 3, maybe $4 a piece for those. So they're not crazy expensive for those. And then again, just wire nuts, finish washers for the backside. There, as you're looking at your project, as you're looking at your test bench, the little finish washers on the backside here, the nylon lock nuts. I like having just a couple of those just to hold it together here. The machine screws, all of those things, then just kind of somewhat self-explanatory. So the overall inventory for this isn't too crazy. Also, I did order. Sometimes you can go to like Michael's or Depot or Hobby Lobby and pick up like 3/16 or the 1/4 inch foam board. I like going to United Suppliers and ordering a case of the 32 by 40 foam board. It's much less expensive. You can get a case of 24 or 25 for like $30 or something like that. I think it was like $30 or $35 for the entire case, which makes it very affordable per sheet. And you can use these. And so what I did then is for the actual test benches or the little test kits that you've got, in the past, I've just done 8.5 by 11, but using the 32 by 40 sheets, an 8 by 10 size, actually work came out, as far as cuts, came out a little bit more efficiently. So there was much less waste, or virtually no waste. And if you're going to ship them in those mailers that I sent to you, an 8 by 10 sheet of these actually fits into the mailer a little bit easier, a lot easier actually, than a full 8.5 by 11 sheet, and gives you a little bit of play in there as well. So there's a little bit more work involved as far as cutting these, because you cutting the printouts a little bit, because you'll have to trim those down from 8.5 by 11 to 8 by 10s, but it seemed to work okay. And so these were some of the materials that we used. And as we go through this, sing out or send me a message or anything like that you can, if you'd like to, as far as questions or suggestions, anything like that. So this is what I had. Just as a little bit of a side note, as I was taking pictures of these to keep the outside two from distorting, they're actually angled in somewhat. When I took the photograph, they're actually angled towards you, and these are actually angled in just slightly there, but these are angled in fairly significantly this way when you're taking the photograph from up above, to make them look like they're all straight up and down as you're taking these kind of photos. If you'd like me to share the manifold pick with you that I've got, I'd be happy to. So this way you can actually use that, or see if you can use one of those to be able to print that off as well. The tools. So with this one here, I purchased an awl that's over there to kind of help punching. That was used to punch holes in I guess in your, over here in the pieces here, and also to kind of punch holes in here where the screws will go. And so that all worked pretty well. Everything fit using that kind of an awl, couple of bucks for one of those. A number 2 Phillips screwdriver. When you're working with those barriers, those like the 6-pin barrier strips, Anything smaller than a number 2 will have a tendency to strip the head. So minimum size of a number 2 Phillips screwdriver on that. A 9mm wrench worked pretty well. Wire cutters. And then I also got some new wire strippers for this one here because of the volume of number of wires that I was going to be stripping with this one. I got one of these that would actually allow you to automatically strip the wires, and that saved a lot of effort, a lot of frustration as far as making sure that all your wires were stripped correctly. And also a heat gun for the for shrinking the heat tubing around the resistors. Okay. All right. Oh, and then I guess back over here, there's also, I purchased for this one here, I purchased 27 ohm resistors and also 33,000 ohm resistors. And we'll talk about that as the reason why I did those. You could also, if you wanted to, possibly purchase like 680 or like a 600 ohm resistor to kind of give you a partial short, which would be kind of also good. But then I'll explain a little bit later why I chose these two here. Okay. All right, so those are used there. So that's a little bit about the tools that was used and the parts that I purchased for this one here. Assembly steps. First was to print the manifolds, then either to cut them to size 8.5 by 11 or 8 by 10, and that included the foam board. Okay, and this time in the past, I have not laminated, or I did not laminate the sheets here, but it just seemed I wanted to try this and see how they shipped, and it seemed like they seemed to do pretty well. I hopefully, and it actually didn't create too much more of a problem as far as I guess punching holes for these things or feeding the wire through or being able to mount anything in here. The lamination didn't create too much of an issue. And this was like 8.5 by sheet lamination sheets, but then I trimmed it fairly close, a little bit closer than what they normally recommend, but I wanted to just kind of see how that would work and to make sure that everything kind of fit fairly flushly. Okay. All right. So then from there, I would laminate these, and then I glued the laminated sheets then to the foam board. I used like a Super 77 or the Elmer's spray. And what I did then is I sprayed both the back of the manifold sheet, and I also sprayed the surface of the foam board. And then within the first 15 seconds, I went ahead and then almost immediately then actually placed or laminated, or I guess place the manifold sheet onto the foam board. And then I punched the holes for the wires and punched the holes for the screws. And that's kind of there. I also had in the process to make it a little bit easier and have a little bit less punch out on the back side of this, is I had a stack of extra foam board here to kind of punch into there, kind of look like that. So all of a sudden you'll have a bunch of this to kind of hold there, and it actually kind of made everything fairly stable as you were kind of punching holes for that. And then also then punch the holes for the screws there, like so. And then after that, so then I punched holes for there. Then from here, what I did is I cut speaker wire to about 3.5 inches long. And there was going to be 2 for each valve. And with what I did here, then all I did was put a resistor in here, and then slid the shrink tubing over the resistor, and then fed these wires into there. And then I hit it with the heat gun. And you could probably hit this if you feel like it actually come loose a little bit, go ahead and hit it with the heat gun again. But the 3-to-1 has a tendency to work much better and actually holds these fairly snugly. But if you start tugging just on the wires themselves, they could actually kind of tug loose a little bit. But that was kind of what I did there. And so this is then going to simulate your different solenoid valve, the solenoids on the valves right there. Okay. And then fed them through the foam board. And then the important thing is to make sure that when you push this through, then make sure that you tug, or if you pull this wire through, pull it through, you pull on the shrink tubing and not the wire there, because you'll have a tendency to maybe pull those out, because this can be fairly snug. And then from there, I cut some little pieces of mat board or some cardboard to kind of put there to kind of help protect the backside of the foam board here. So this way, this wouldn't actually pull through the foam board, and it actually kind of gave it a stable part to kind of work against there. And so I did that for each of those different wires there, just to kind of stabilize it a little bit. Okay. Now from here, this is just kind of optional. You wouldn't necessarily have to do this, but I was a little bit OCD, but I wanted to make sure that everything stayed fairly flush. So then if you take a peek then on the underside where these two, where the resistors and the other kind of rest against that back piece of foam board, what I did then is there's some different ways you could cut this out, but what I did is I used a router. So I made a jig, it's not a great jig, but I cut it out of some 1x material here, and then put a little edging around it. And what this looks like is, I'm going to just real quick, is what that looks like. It looks like this. So I went ahead and I cut out, these are really sloppy looking, but these are my kind of my jig areas here for my template, for my router bit. And then I went ahead and put a little bit of an edge around here, and that's where the foam board would then sit into. You could actually place the piece of foam board, it would actually stick out above it. So this way you could just lay this on the table and then get you a router. If you wanted to go to this kind of effort, you wouldn't necessarily have to do this. But I got a 3/4 inch router bit like this with a bearing on it. And so then this bearing would then just ride around on the insides of that and then just trim out a little bit of the foam. And this kind of gave it just a little bit of a recess to allow you to have a flush fit between the two pieces of foam board. So maybe a little bit too much if you guys, but that was kind of what I did with this one here. This one here, you can kind of see it kind of snagged it a few times there, but it seemed to work pretty well. And it probably took me longer to set up the jig than it actually did to trim out all of the foam board. So within the thing, probably a couple of hours total for all of that there. Okay. And so those are a little bit about that there. And okay. And then from here, so that's what I did there. And so then I went ahead, and that was the bit that I had. It's kind of a flush cut bit with a bearing on it. And then just worked it around inside of each one of those holes, and it seemed to work pretty well. And worked out okay. And like I said, didn't take very long once you got everything set up that way. Okay. And then moving on. And so then once I got that done, then the next step, once you get those things trimmed out, if you wanted to do that, then the next thing would be to mount the foam boards. And that's a matter of then just pressing these in. Fortunately, all of those there's a little metal posts on the back of these terminal strips, and they'll actually pop into that. So they actually hold this terminal strip in place into this. And so then once you've got those holes punched using your awl, you just feed those screws through the back here, and then just get your screwdriver and tighten it up with your wrench, and the two of those snug it up, and they actually hold it together pretty darn well. The first ones that I used to have like screws up here and then screws down at the bottom, but it just didn't seem necessary to have that extra work down here. So you just didn't seem to need to do that. So if you have suggestions as far as how you think it might be a little bit better, more of an interesting way to do that, or a better way, I'm completely open to suggestions there. Okay, then cut your wire. And here's all the different lengths that I have that I cut. 6.5 inch yellow, green, 7.5 inch or 7-inch 7s, 3.5 inch blue, and whites. Then you'll use the most of these. So you're going to need, if you need anything, you need a lot of white wire that you're going to be using for the commons, and then you'll need everything else there. But this is, you use the most of the whites, the white wires there, because actually you have some 3.5 inch pieces. And actually, I forgot to actually label that, but you'll also have like a 3.5 or probably like a 4-inch piece of white wire as well there too. Okay, so those are some of the other parts that we had. And then you just, once you're done with that, then you can assemble it and put it together, and then you're ready to go. And it works pretty well. And so hopefully then if depending on how many you make, once you kind of get that, once you understand what you're trying to do, kind of works pretty well. Okay. And then from there, then just be prepared for assembly line work. And so then as you get through it, you'll start kind of getting into a rhythm. And next thing you know, it's 2 a.m. and you're still cutting wires, or you're watching a movie while you're cutting wires or something like that. So it can be kind of interesting to do. It's just arts and crafts to a certain degree. So it actually works out pretty well. So, but then you'll kind of get into a rhythm, and depending on how many students you have, you can use these multiple times. I've had these, like I said, my initial ones without lamination have lasted at least 2 or 3 years, a couple of years at least, for a number of classes. And so if you laminate them, should work out even better, I'm thinking. So we'll kind of see. Okay. All right. So that's a little bit about construction. Any questions, comments, or anything, any other kind of or questions about that, about the process? I just wanted to kind of just share that with you, so this way you have an idea of what I did. And feel free to copy that exactly how I did it, or if you've got some other things, please do not hesitate. I'm here to kind of help all of us just kind of try different things. So, teaching moments.
Brad, what was your overall cost per unit?
Oh, good question. And so that was something I didn't have a chance to tally up, but actually it was, if you count, let's see, I was trying to think, about $20 a unit if you count, or less, actually less than $20 a unit, counting the multimeter. The multimeter cost about $7. That was probably the most expensive thing. Then you've got about a $3 terminal strip, so that's about $10. Then everything else cost about 10 total. So I'm thinking about $20 per, if not a little bit less on that one there. So good question, Lindsay. I'll have to go back through and look at my numbers, but I can get you a better number than there. I was just but that's about what I was estimating. It was about $20 a piece on those, I'm thinking. So good question, but that was something I should have had. That was one of the things I didn't quite have a chance to get a total on that one, but good question. So, but I'll work on that. Okay, so teaching moments, things that you can do then with this would be having the students learn how to use the multimeter, understanding electric measurements and their uses for what we do. Another one, simplifying the troubleshooting process, or at least having them have a much more tangible idea of how to troubleshoot some of these things. And then, especially if you're limited with the number of valves and solenoids and controllers that you have, this may be something that you can do with that. Okay, and then also helping them to do some critical thinking using the process of elimination, and there may be a whole other bunch of things that you guys think of today as we're kind of going through this. Okay, all right. So first teaching moment: basic meter operation. And so then, let's go ahead and let's make sure that everybody's whoever's got it. If you got them with you, then is to go ahead and let's go ahead and let's check out our multimeters and make sure that they're operating correctly. And I've got a couple of camera options that we can do on this one here. So this is our multimeter. And one of the things that what we want to do then would be, the first thing is, let's go ahead and turn your multimeter on, make sure that it's operating. Okay, you should get 0 or something close to 0 when we first fire it up. What I'd like you to do then is turn the dial down to, we got ohms, so we have ohms on the bottom, we have DC volts over here, AC over here, so we will primarily be working with ohms or resistance down over here. Okay, and so then go ahead and turn it to 200 ohms, which means that right now this multimeter would then measure anything between 0 and 200 ohms. Anything outside of that then would act like an open, and this essentially a 1 with a dot here for this particular meter tells us that we have an open circuit. There is a break in the line, or there is a break in continuity. So one of the things that we could do then is, let's test the precision of our multimeter. So we cross the leads and we go ahead and let's see how precise are these multimeters. Now mine right now, it's kind of bouncing around a little bit, and you can expect that, but it'll go down to about 0.6. And so then a 0.6 for this particular meter then is telling us that when you get a short reading, it may read at the lowest that it may ever read would be like 0.5 or 0.6. The other meter that I was just using probably an hour ago, the lowest that it would read was like 1.3. So John or Lindsay or any of you guys out there, what'd you guys get for readings on that? Just kind of yell out. What'd you guys get for kind of a zeroed out reading?
Yeah, it was 1.2 for me.
1.2. Okay. Douglas, how about you? What'd you get? Or let's see, who else has got theirs with them?
I got a 1.4.
1.4. Okay. Anybody else?
1.5.
1.5.
1.7.
Okay. So we're getting them all over the board. So what that number is going to tell you then is that if you're measuring a short, you'll probably need to expect nothing less than that. Ideally, with a shorted circuit, perfect. Okay. All right. So with a shorted circuit, like with April, you would get like a 1.1. Daniel would be like a 1.0. So then normally we would, in an ideal situation, we would want to expect 0.0. But in this case here, your meters are precise, or their precision is down to about 1.1 or something like that. So then if we're looking for a short, that's what you could potentially expect. Okay, cool. All right. So this is a little bit about this meter here. And so primarily we're going to be working with ohms over here. We might tinker a little bit with DC volts here, but if we were going to be testing to see if you're getting a signal from the controller to the solenoid, you would actually look for AC volts over here, depending on, or unless it's a DC latching system that you're working with. But these are the ones that we would primarily work with when doing some of our troubleshooting. Okay. All right. So just a little bit about that. All right. Things also then, if you haven't done this kind of a work with your students in the past, then what you could do is, just like I have in this photo here, is if you want to do, just have them work with some batteries and see, you know, when you have a battery tester, you're finding out, you know, is it actually delivering 1.5 volts or the number of volts that it's supposed to. And so you could actually set this at 20 volts DC, put a lead on each of the ends of a battery and do that. Oftentimes what I'll do here is I'll go to the mail room where they have like a recycling bucket and there's a whole bunch of batteries in there, and I'll scoop them up and then I'll just take them to class. And it's like, okay, tell me what are the voltages? Is this considered good, bad, indifferent? I may even have taped them together so that they have batteries in series, batteries in parallel, and just be able to use some of those old batteries and kind of help them understand how to evaluate, you know, battery life, or how good the batteries are, those kinds of things. Okay. All right. Moving on. All right. Current. So when you're teaching students about electricity, it's going to be very similar. There's a lot of similarities between how electrons flow and how water flows. So then one of the things to maybe talk to that we're not going to actually get into in this particular presentation is current. If we were working with two wire systems, we would be almost living in the current area, kind of a thing. But we're going to be dealing a little bit more on the other side with amps, or with ohms, and a little bit of voltage. And so current, if you remember that, this is considered flow. This is how many. So remember, so if you're talking about, well, this thing delivers 22 amps, okay, that's telling you how many electrons, the total volume of electrons that are moving along that particular conductor, or how much water is flowing in a pipe. Okay, so that's current. Okay, how much the water is, how flow. So this is why. So this way, if you're operating a super huge piece of electrical equipment, let's say something like a table saw or something like that, and you've got tiny extension cord hooked up to it, you're going to cause more problems, because that table saw has a huge, I guess it has a huge desire, or has a huge desire for a lot of electrons, and it's going to only get a few at a time if you've got a tiny wire, if it's trying to deliver it through tiny wires. So current is flow. Okay. All right. Voltage in this case then is pressure. How much pressure are we having? So then voltage is, so you may have, I've got 1 amp and it's at 4,000 volts, telling you that you've got these many electrons and they're being pushed this hard based on voltage. Okay, so that's what voltage is. Okay, so it measures the strength of the flow. Okay, so like if we're doing a pressure reading, static pressure reading on a house, that would be the same thing as us putting the 2 plugs into a light socket and finding out what the pressure is there in the light socket with one of these things. Okay, so that's pressure. And as we can kind of see here, here's 2 different batteries. Here's a good battery measuring 1.2 or 1.59 volts, compared to a not so good battery that's it's got very little pressure. There's just not much left pushing those, whatever's left in there, whatever electrons are left in that battery, there's not much oomph to get them out of the battery. And so we're only looking at 0.6 volts. Okay. Or this one here, this would be another one. This is kind of like, wow, that's a little bit odd, a little bit high for whatever we're doing. But the kicker is on this one here is I've got it hooked up to AC instead of DC. I've got this one hooked up to AC, so you're going to get a funky reading when looking at that. So it's always important. Working with batteries, you're dealing with DC. When you're working with plugins, you're working with AC. Okay, resistance finally is then just the measure of the slowing of movements of electrons. Is that pipe that we're working with on our irrigation system, are the pipes pinched because of roots or something or whatever, or got a kink in it? Same thing here. Okay, so we're going to be looking at ohms as far as that goes. Okay, so a little bit of, so there's something you can kind of share with your students if you haven't already done so. All right, voltage measurements. Again, one of the things that we could do then would be to test voltage this way. And the things that we're going to be dealing with the most then would be when we're doing troubleshooting is power in, power out. Do we have power to the controller? And that would be a matter of then just checking the actual plug that it's plugged into, and are we getting 115 to 120 volts AC at the source? And then are we getting, if that valve is not operating, are we getting 24 to 28 volts to the valves? And so that was those are a couple of the standard volumes or pressures that we would be working with. Okay, so resistance measurements when we're testing solenoids. Most of the solenoids in our industry then are going to have a normal or a nominal ohm reading or measurement of between 20 and 60 ohms, or maybe 18 to 60 ohms. Anything outside of that range then is going to tell you that something isn't quite right with that particular solenoid. Okay, all right. So that's one of the things. So that's kind of what we're looking at. This one here, this Rainbird solenoid that we're looking at here, it's at 41.4. Cool. It's very good. It's good to go. So we would be able to find out what's going on with that. And that's something that we're going to be doing with this little test card, this little test set, is testing resistances and continuity with different circuits. And essentially, we're going to be simulating testing solenoids. Okay, so let's check our multimeter. We just did that. We were able to find out what's the precision of our multimeter that we've got. Okay, so any questions there, comments, a little bit about or suggestions, or any how have any of you, I guess, talked about voltage or amperage or resistance? I'd be kind of curious. Is anything else, I guess, how do you guys share that with your students? I'd be very interested. That'd be something we can either talk about it now or we can talk about it a little bit later, but kind of think about that one. I'd love to hear if there's better ways to explain that. I'd love it. Okay, so system wiring overview. This is kind of what our little test card looks like as a wiring diagram. We have our controller or this is where all our wires are hooked up to, and then we have our 4 solenoids or our 4 valves here. And that's essentially what we've got on our cards. Okay, so this is what we've got. And we're looking at this here, and I'm going to go ahead and hide this. Okay, so, and if you can kind of see here, this is kind of our control panel up here, and then we've got all our different wires running through our different valves and solenoids here. And so station 4, station 3, station 2, station 1, and here's our common wire return coming back over to here. Okay, now, one of the things that I wanted to kind of share with you on this one here is there's a learning moment here. Maybe it's just me, but even in the Air Force or just in any time that I try to do this, when you're hooking up wiring to a controller, one of the things that you might notice is all of the wires are coming in on the left side of the screw. What's the reason? Why would we want to mount the wires on the left side of the screw? Or on the 9 o'clock side?
When you tighten down the screw, it goes clockwise.
Absolutely. And so this is key. And so then that's exactly right, as if we put the wire here on the left side, and as we tighten this screw down, it's going to actually pull this up tighter into the screw, making it a much better connection and a much more viable, less likely for arc or anything else like that. If you mount it on this side, it's going to have a tendency to want to push the wire away. So whether you're doing wiring with controllers like this, so thanks, that was great, so spot on. So whether we're like this, or if you're wiring, let's say rewiring a plug, or you're building that part, because some of the controllers that we receive don't necessarily have external wiring hooked up to it. So you may need to hook up a plug or a connector to an extension cord or to a cord or whatever it is. And so it's just as important to make sure that with your black, your white, and your green wires, that you wrap it around so that it's traveling clockwise. So when you screw that screw in, it's going to tighten it up and make sure that it's a little bit more secure connection there. Very good. Well done. So good.
Brad?
Yes, sir.
When I do it, I often will make a U on the wire. Does it matter?
If you're actually in the control box, I don't know if it would necessarily matter there because you may not have a lot of pull or tug, but anywhere else, I normally do that. Sometimes for simplicity's sake, I don't do a U, or I guess just for in these areas here, I don't, but it would be very easy for a person to do that. With this right here, you could actually explain to them that you could either keep it straight or do a U. If you keep it straight, it makes it much easier to actually remove the wires at this point once you loosen them up. But if you look into a lot of controllers, especially in golf, where you're using like 10 or 12 gauge wire, sometimes it's very difficult to actually get those wires kind of bent like that and be able to work with them a little. It makes them very difficult to work with.
Okay.
So, but in a control setting like this, where you're not going to have a lot of pulling going on, I wouldn't do it. I wouldn't. You could, but you wouldn't necessarily have to. If it's a plug, if it's an extension cord plug or a wiring plug or a connector, absolutely. Anything that you can do to kind of help solidify this, or if you're working with house wiring, I always try to twist them around there. But within a controller like this, normally you don't necessarily have to, but it doesn't hurt.
Thanks.
So good question. Another good question. Okay. All right. So another teaching moment, system wiring here. All right. So for the valve to operate electrically, there must be a complete circuit. So you must have a circuit where the energy or the electrons are going to flow here. They're going to go through the solenoid back this way along a common circuit back to the controller. So you have constant flow traveling through. You need a complete circuit. Okay. And so that would look like, let's say this one here, station 2. So it's traveling. We've got 24 volts AC traveling to the solenoid down through the windings of the solenoid here. It energizes the plunger, if it's working correctly, up and out and back down across the, back along the common wire, the return wire here. And remember, that's key. Knowing your order of operation becomes very critical when you're doing troubleshooting. So whether it's electrical like this, or if you're teaching them how the operation of a valve is, or a valve and head sprinkler for like golf, all of the order of operation then becomes critical as far as being able to do that. So one of the first things that we would test, power in, power out. Do we have continuity? Do we actually have power flowing completely through this? And then we can make our evaluations from there. Okay, so whether it's that one there, or if it's station 4 over here, be the same thing. We're looking at the same travel. So it's coming down through here. It's going to go through the solenoid, through the windings, back out and along all of these over here and back to our control panel here. Okay, so that would be a good teaching moment, at least letting them know about kind of understanding continuity. Okay, all right, and oops, and boom. All right, so electrical readings. So what we're going to do next then is we are going to actually then kind of let's get active and start working on our test cards here. So here's our test card. And let's say, if anything, right now we're just kind of getting to know this. And so this will kind of help us to determine if the test card that you had actually made the trip okay, and if I built them correctly. So, and I tested all of these, so they should be okay. What I'd like you to do then is let's go ahead and let's turn on, go ahead and turn on your multimeters. And I'm going to switch cameras to this one here. All right, so here we are. Oops. Okay, so here we are. And so I'm going to go ahead and turn my meter on. And so we're going to test each of these. And so it's like we were actually testing circuits and seeing what how the solenoids are doing. So with this first one here, we've got our, go ahead and put the black lead on the common right there. And then from here, then just go ahead, once you've got your multimeter set up to 200 ohms, that's the range that we're going to be dealing with. And so then we can then just see what our valve is reading. And so essentially that's resistor number 1, or valve or solenoid number 1 is giving us 27.7 ohms. Good, bad, or indifferent? Is that within range? You bet. So number one looks good. All right, let's move it over to number two. So all we have to do then in this case here is we can leave the black on there. Go ahead and let's touch number two. And I've got 28.1. It's a little bit different than the other one, but good, bad, and different. Is that a good one? So 28 ohms. How are you guys doing? Are you guys getting similar readings, I hope? Okay. Okay, so I got about 28 ohms, 28.2, perfect.
I got a 1 on.
You got one?
On the 2, yeah.
Oh, okay, so it's, let's see, so if you've got a 1, that means it's like a 1 with a dot.
Yes.
Okay, that means we have an open on that one there. So we need to kind of double check and make sure that all of your wires are connected. You could even, like, if you need to, for number 2, kind of maybe jiggle this one just a little bit, jiggle the wire nut here, make sure that this is connected okay. If you need to, kind of twist it clockwise just a little bit. And then also maybe twist these two right here a little bit clockwise, see if that helps a little bit. Any luck?
Not so far, but
Okay. Okay, but number 1 worked okay?
yeah, number 1 was 27.
Okay. All right. Trying to see. Anything?
Nope.
Okay. Next thing is down at the base.
Oh, wait, I gotta rewire when I moved it a little bit and the whole thing came apart.
Okay. Perfect. Great. Yeah, that's kind of great, but that's kind of
It solved the problem.
that's good. But actually, so sometimes making the trip, sometimes they survive the trip, sometimes they don't. That's but actually, it's a great troubleshooting exercise.
My
Anybody
box
else?
came very beat up. It looked
Did it?
like it ran over with a truck.
Oh shoot.
Okay.
So I'll have to come up with a better way to ship those a little bit more.
I'm still getting a 1 though.
Still getting a 1.
Yeah, and I rewired it.
Okay. Let's see. Go ahead and if you need to, right at the base where the heat shrink is kind of coming up out of the paper.
Yeah.
Kind of twist those a little bit. Just kind of twist them lightly with your fingers.
Okay.
And see if that might help you a little bit.
Yes, that got me 27.6.
Perfect. Okay, so that's gonna the way those wires are kind of the resistor wires and the speaker wires. They're being held together. They're just being held together just by the heat shrink right there. And so sometimes they might work their way a little bit loose. So, and if you need to, just maybe twist those wires just a little bit, and you should be able to get continuity back. Good. So I'm glad it's working. Well, actually, I'm glad somebody had an issue so we could actually kind of go through that together. So excellent, excellent, excellent. Okay, moving on to number 3. So let's move to number 3. All right. What'd you all get with this one? I got a 0.4.
I got a 1.0.
Okay. Okay, and a 1.7. All right, I gotta see that Tina had a 1.7. Good. All right. With this one here, then hopefully you don't get some kind of a different resistance reading on this one here. So Yvette she got 2.8. All right. So this one here, all it is it's just straight wire. It's just straight wire. There's no other connection there coming through here. So this one is supposed to then represent a shorted circuit. And so if you get a shorted circuit, David was asking if there's any reason why I didn't solder the wires before I did the heat shrink. Was yes. It was one more step in the manufacturing process. I thought about doing soldering, and chances are I may do that in the future, but to do them a little bit more, because I debated on that one quite a bit. And so I decided not to and just rely on the heat shrink to be able to maintain continuity. But yes, you could have definitely soldered those fairly easily. So good question, David. Good question. Good question. Good question. That's a thumbs up. Okay. All right. So that one there should be a 0. You should have about a 0. So that would essentially, so when you're having them go through here and you would say, oh, you've got a different reading. On this one here, what do you got? Well, that's a shorted circuit. So that's telling you that there's a short somewhere. Chances are there's a short, probably you got a bad solenoid and it's giving you a shorted reading there. Okay. Now on the next one, let's go ahead and let's move it to number 4. All right. Hopefully now we should get a 1 or an open reading on this one here. Hopefully you guys are getting a 1 with a dot. Okay. Now this one here, this one. So what we're looking at, this one here is right now you could do this a couple of ways. Well, gosh, we have an open on this one. Now, it could be another thing if you actually happen to be working with some golf course guys or with some Toro solenoids, they have a solenoid, it's called a spike guard solenoid that is rated at 33,000 ohms instead of just 27 ohms. Okay, so what I'd like you to do then is just turn your range to 200,000. And now instead of it reading just from 0 to 200, now it's going to read all the way from 0 to 200,000. So what we're reading here then is actually about 33,000 ohms. Now you may get anywhere between 29, you may get a reading between 29 and 34 with this one here. Did you guys get a slightly different reading once you moved it to 200,000?
32.6.
Okay, 30, perfect, great. Good. And so this is one way to teach them. So whether you had if you installed a 33,000 ohm resistor in here, you could also install, you could install, let's say, a 600 ohm resistor in there, which could then indicate, instead of it indicating an open or a different kind of solenoid, a 600 ohm resistor could maybe then tell you that it's a partial short, that maybe there's a bad connection somewhere and that wire is touching the ground outside, or it got wet. And so that the waterproof circuit is no longer very good. And it's giving you kind of a partial short, or a partial, kind of a partial funky reading. And so this is one way to kind of force them to kind of think about that. It's like, oh, just because it's an open doesn't necessarily mean it's a complete open. To make them take an extra step and go from here, and it's like, well, does it give me a reading here? No, that's 0 to 2,000. Here's 0 to 20,000, still open. But then once I go to 0 to 200,000, aha, I've got a 33,000 ohm resistance reading here. And it may force you to ask questions. Where that may force you to ask question as far as, okay, what type of system do you have? What type of solenoids are they using? Is it a Toro system? Is it a Toro system that actually used to be a golf, or they were using some valve and head sprinklers or something like that? Any of those kinds of things that may actually at least force you to ask some questions there as far as that or anything. So, but this is one way to kind of get them thinking a little bit more critically, that it's just not either, it's just not a short and it's just not an open. Okay, and they might have to kind of take another look at that. So we had 2 circuits that were good, and then we had an open circuit. We had a shorted circuit, and we have an open circuit. But that open circuit could then also be read or interpreted as maybe it's got a different kind of a solenoid on it. Okay, different technologies that are being used. Okay, all right, moving on. All right, so those are some of the things that you can do to test, or the way we can kind of use this particular test bench, or this little test card. And so then you can do that. There's some other things that we can do that we're going to be kind of working on here in a second. So, all right. So then on the first one there, when we were looking at our readings, again, so this would be one way to kind of show them, this is the range. So from 0 to 200, we're reading right here. So we're in that range. And so it's going to look pretty good. Okay. Go to the next one. Oh, and so then either 1 or 2 are going to give you that same kind of a reading. Okay. Where that's short, it's going to give us like 1 to 9 ohms or less. And that's kind of, let's say we have a short circuit there, or we got a short circuit going through the solenoid here. Okay. Wires are touching within the winding. Something went bad. Okay. And so that would show you where a reading's like here. Now, what I'd like you to do next is go ahead and, oops, I didn't want to do that. switch the camera, let's go back to this one here, is, okay, is move this back over to, oops. So move this one back over to 1, move it back over to station 1, get your normal, get your normal reading here. Here's our normal reading, or somewhat normal reading. Mine's kind of bouncing around just a little bit. Okay, and then move it all the way to 200,000 and you get 0. So if you have this at its wrong setting, if it's not an auto ranging multimeter and they still have it set here, they're going to read this as a short, which would then give them the wrong reading. So it's important to make sure that you have this set up correctly, and that you're also then reading the correct thing here. So that can also give you an oddball reading. And so that would be something, if you're doing a quiz or something like that, and you're handing these things out, or whatever it is, have these multimeters set up at 200,000 and say, okay, test these and tell me, is it an open, a short, or is it operating properly? And if they forgot to move this back down over to here, they're going to get an erroneous reading, and that would be one way to kind of test them, to test their knowledge of the use of a multimeter, and a little bit of critical thinking skills there as well. Okay, all right. Okay, all right. So that's a little bit about that one there. Okay, and then oops. Okay. And an open, we kind of looked at the open, and that would have been this one here, and it would look like it means we have a break in the line somewhere, or let's say a break here. We're hoping that it's in the solenoid itself. Okay, and so then we're testing that. So we just did some testing with that one there as well. Okay, and so that's showing us then we have a range of 0 to 200, but the reading that we're getting is out here. It's infinite, and that we're not getting any kind of reading whatsoever there. Okay, is what that's appearing to be until we dial it in. There's 200,000 K or 200K, and then there's 2,000 K. And so that would still kind of show that kind of the same kind of an opening there as well. And actually at 200K, we should have actually got a reading. We would have got that reading here instead of out here. So, so don't let that mislead you. So then so this is almost too big of a reading because our reading's right here. And so 200,000 K would have been fine, but then the 2 million K, or basically 2 million ohms, would have been way too large. Never mind. So I might have that set up just a little bit incorrectly. Okay. All right. So partial shorts, again, this is what I was talking to you about before. Maybe you got a bad splice, maybe wherever they were going in the valve box themselves, and maybe where they were putting the wire nuts together, and those things, they would have been, maybe one of the wire connectors has gone bad, or it's starting to leak water, or there's a bad splice there, or whatever it might be. That might be in that something's leaking to ground, giving us a little bit more resistance than what we should have been expecting. And so this is where you could maybe install a different kind of a resistor in there to kind of give them more of a partial short or a bad splice kind of a reading there as well. You could do something like that. Okay, all right. Moving on. So my station won't operate correctly. Oh my goodness, what do we do? And let's say they go out there, you've got a client that comes out and they say, you know what, I turned my controller on and station 1 isn't working, or station 2 isn't working, you know, those kinds of things. What can we do to help teach troubleshooting with this? Okay, so remember, when you're troubleshooting these things, a teaching moment, this would be a good test question or a quiz question then, is what are the 3 things that you can do to do this, to be able to test or do troubleshooting? Okay, there's only 3 electrical components to consider in this case here: the controller, the wire, and the valve or the solenoid. Okay, those would be the 3 things to do. And so step 1 is, you might just ask them, in order of importance, what are the things that we do? Well, first I want to check power in, power out. That would be like we're water in, water out. Well, the sprinkler system isn't working. Well, is the water turned on? Well, you know, that'd be one thing. Or is the electricity turned on or off? I had a student, poor student, he was working on he was hooking up a controller with some irrigation and everything else like that. Everything was hooked up fine, but he never turned the water on. And so once he realized that he turned the water on, then then everything worked out just fine. So same thing here. We check the controller, we could check the wire and the valve. Okay, so power in, power out. One of the things that we can do with this, we can't really check power in or power out with the way I've got this one set up here. However, there is something that I was kind of tinkering with that I wanted to share with you here, and I'm going to stop sharing that. I'm going to go to this. This is something else that I just built this a little bit ago, and I wanted to kind of share this with you. Is instead of using this one here, if you wanted to use, in this case here, I've got 3 9-volt batteries. Okay, and I've got them, the way I've got them connected like that, I've got them hooked in series. And so if I've got 3 9-volt batteries hooked in series, that gives us about 24 volts DC. Okay, and so we've got one here, it's kind of connected to this one, connected to this one here. So you've got 9 plus 9 plus 9 gives us 27 volts DC. Okay, and so this might be something that you can connect. Now, question for you, when we're testing AC voltage with the controller, okay, should the, normally when we do that, okay, that's a little bit different than checking our resistance, like checking the solenoid, the resistance of the solenoid. When we're checking the resistance of a solenoid, we need to have the power turned on or turned off of the controller. Which one is it? On or off? If we're checking the resistance. Right, Dave, we need to have the controller turned off. Off. Very good, thank you. So what you're gonna wanna do, if you build these little tests here, what I'd like you to do then, what I would do is I'd move this over to 200 volts DC, and let's say, okay, well, we want to test power in. Well, you can then just go on over here and check and see, well, do we have power in? Yes, we've got about 29 volts to here, so we have 29 volts coming to the controller, or at least the panel, so that's okay. So the controller's okay. Now we just need to check and see what's going on then with everything downstream. Now, if you decide to do this with your own, make sure you disconnect these. I did this just a little while ago, and I actually, these 3 batteries fried that first resistor. It started smoking and smelling pretty bad. So that would definitely be a telltale for you on that one there. Okay, so remember, when you're dealing with this, you always, if you're checking electrical voltage on a controller, make sure you have your meter off, because otherwise you'll get some erroneous readings and you could actually burn up your multimeter that way too when you're checking voltages. Okay, like that. Okay. So, or when you're checking resistance, make sure that the power of the controller is off. That's the key. Okay, sorry, I didn't mean to confuse you there. All right, so that's a little bit about that one there. Back to this. Okay, now, all right, back to, okay, so let's say we checked this, we said that's okay. We checked the voltage AC, that's okay. Let's say we check the start time, water days, everything in the programming of the controller is okay. Sensors and moisture sensors, rain and moisture sensors are all okay. Let's say all of these checked out fine. And so it's going to leave us then with what's going on with our solenoids here. Okay, and that's what we just did. Is you would also want to check the fuses on your controller, make sure everything is good there. Otherwise you can spend a lot of time if it's just a fuse. Make sure all the fuses and fusible linkages are actually good there as well. Okay. All right. So what we just did then is we looked for, when we were just kind of going through that, we found our resistance measurements. Which ones were good, which ones were shorted, which ones were open. Okay. So one of the next things that what we're going to do then is what happens if we have a hot station, if we wanted to try to isolate which station is bad, okay? Or is it more than one station? Or is it the hot wire? Or is it the common wire? What we'll do then here is what I'd like you to do is go ahead and disconnect the, go ahead and disconnect the blue wire. Okay, so go ahead and disconnect that wire here. Okay. And so what I'd like you to do here then is go ahead and then make sure your multimeter is set to 200 ohms. And let's check each of our stations. So if the station wire, if the number 2 station wire is broke somewhere or cut, what kind of reading do we get there? We get that open. We get an open. There's a break in the line. Okay. And like, okay, so at least we know, we know, well, number 1 isn't operating correctly. Is it the common or is it the hot wire? Well, let's check and see what's going on with station 2. So go ahead and check station 2. And hopefully then you should get some kind of a reading. So if you think about it, this circuit is broken, but this circuit is still traveling all the way through over here. So that circuit's good. Circuit 3.
Oh, my comment's good.
So this one here, it's a short, but otherwise it's operating correctly. If we would have had a resistor there, we would have the standard reading. So that was the reading that we expected there. So that one's actually working correctly. So station 3 is working okay. Okay. And then we could finally move over to station 4. We have an open, or if we switch it over to here, we have 33,000 ohms. So station 1 is not working correctly, but station 2, 3, and 4 are operating as they had been before. Okay, so we could then definitely isolate. It's like, well, you know what? It's not a common wire problem, but it's a station wire problem, and it's a station wire problem with only station 1. And so those are the kind of readings that you could get. And this is something you could have the students then go through in class, is make a break and then do that. So go ahead, if you can, go ahead and reconnect those wires as best you can. Get those connected back up, and we will go ahead and retest it. Make sure we're okay. And I've got an open. Let me double check here, make sure we're good. Okay. I got kind of a resistance back. It's bouncing around just a little bit, but it's okay. Thanks. Okay. There we go. That's a little bit better. Okay, so that one should be working again. So that would be one thing that you could do with this then to test them. You could show them then, okay, if you've got a bad station wire, this is how to isolate and how to troubleshoot a bad station wire compared to a common wire. Okay, all right. Next one, let's go to the next one. And, oops, wrong one. Go back up here. Go to this one here. And oops. Okay, so there's our break in the blue wire there, and that's what we just tested, and we tested each one of those. And so we got okay, and so then we've got a short there. We've got open, regular, regular, and regular. Okay, so this one's bad, but all 3 of these are good. That would be one thing that we could look at, is how to test a hot wire. All right, common wire before the first valve. Now let's go ahead and let's check this one out. So let's say we have, now let's say we went through all of that and we're still having some problems. And so let's say we go in and we still have an open. So what I'd like you to do on this next one then is go ahead and disconnect. Go ahead and disconnect this white wire here. This white wire here on this wire nut here is, go ahead and disconnect this one. Like so. Okay, so disconnect that one, and then we can then test all of these and see what we get for continuity to see what's going on with this. And this will give them an idea to understand that. So we've got this, and then we could test, oops, here. And so this one's an open. This one's an open. Number 2 is an open. Number 3 is an open. And number 4 is also an open. So if you tested all of those and you had an open circuit on all of your stations that's in that particular system, then this would at least tell you that you've got a break in the common wire somewhere between valve number 1 and the controller here. That would be one way to kind of show that. This would be one way to kind of isolate that, that kind of a problem. This might give them an idea of how to kind of visually understand how that works. Okay. All right. So what I'd like you to do next then is go ahead and reconnect those 2 wires. Like so. And with this one here, we could actually do a number of different ones. We could actually disconnect the one on the blue or this one here, let's go ahead and what I'd like you to do is go ahead and off of solenoid number 2, go ahead and disconnect this one here. Go ahead and disconnect this like so. Okay, so we're going to disconnect this one here. All right, and so this would be, this is I'm trying to isolate a wire, a common wire after, let's say, the first station or at a different station there. So now let's go back, and so now we've got here, we can check station 1. And we're getting our voltage, we're getting our standard ohms reading. Oops, out of focus. But the current or the circuit is running through here. It's going back this way, and it's got a complete circuit there. Oh, thanks, Douglas. Thanks for coming in. Okay, and that one's there. And then we can also then check station 2. That's odd. Let's see. Oh, I got this one. This one's still touching there. Whoops. Okay, so we got a break there. That's better. So we should be something like that. Okay, we definitely need a break here, and so station 2 would be open. Oops, out of focus. Out of focus. There we go. And then station 3 should also be open, and station 4 then should also be open. And you could break that line anywhere you wanted to. When you're working with the students, you could either do a break here, you could do a break there, you could do a break here, wherever you wanted to be able to kind of have them isolate or see where it is, where station number 1's working fine, station 2 is working fine, but station 3 and 4 are not working fine. So you could ask them, where is the break in the line? Well, it's in the common run between stations 2 and 4. And so if they're out there in the field, at least they would have an idea of where to start looking out there to figure out where that break in the wire might have been. Maybe they were doing some digging between stations 3 and 4, or 1 and 2, or whatever it might be. That kind of a thing there. So this would be one way to kind of work with that. Okay. So,
Brad, I think what you actually just did was a good teaching moment too, with the wire still connected to valve 2, the common wire connected to it, but it also being disconnected on the other side. That commonly happens where the wire pops out of the wire nut and you don't know it, and the actual problem is in valve number 2 with the continuation in the common wire. So it's a good teaching moment too.
Yeah, actually, you're right. Perfect. So there you go. See, I love this part. This is where you can kind of learn stuff like that. And it's just sometimes by accident, but those are some things that you could then do with that. And so awesome. Yes. Great. Good. Cool. So yes, and that's what I loved. So there's some different things you could kind of do, play around with these a little bit and kind of see what you think on what you could kind of tinker with on that. You could even, if you wanted to, you could actually wire these all up to be all good solenoids or something, and then kind of be creative with something else on how you would want to do that. Now, there is another thing that I'd kind of like to skip because I think we're running out of time. But what I'd like to also show you is what kind of resistance readings do you get if you hook, let's say they've got 2 stations hooked up to or 2 valves hooked up to 1 station, and you could kind of help to determine, is it hooked? What kind of funny readings are we getting? Are the valves hooked up in series, or are they hooked up in parallel? And most often, if you have, let's say you had 1 through 4, and all of a sudden they added a 5th station. How did they wire that one in instead of having to run wire all the way back to the controller? All they did was just kind of piggyback off of another station. Okay. Well, you could kind of figure out what kind of resistance readings could I expect, and be able to have a better understanding of, okay, well, they hooked it in series versus hooked it in parallel. Okay, so I'm going to go ahead, let's go ahead and hook these up so we can do that. So I'm going to pop up that particular screen. I'm going to skip ahead a little bit here and get us to, okay, so that we just did those. We just did the breaks, the wire break there, and we also did a wire break there. And so you'll have that in the PowerPoint. Okay. The ground fault, not going to worry about much right now. And there's some solenoid stuff. Unfamiliar readings with multiple valves. So is it single, is it parallel, or is it series? So what I'd like to do with this first one is a parallel circuit. So this one's a little bit challenging. What I'd like you to do then is what we're going to do is to do this. I need to switch cameras and stop sharing. And I'm going to switch cameras. And what I'd like you to do then is how to connect these is if it's hooked in parallel, what you need to do then is hook these. So with stations 1 and 2 is you're going to hook the two left black wires together, okay, and the two right wires together and the two left wires together here. So what you're going to do then is you would disconnect the wiring here and disconnect this here. And so then what I'd like you to do is, don't worry, let station 2 go for this point. And let's say we're going to run these two valves off of station 1. Okay. And so to do that, we're going to hook up 2 of the black wires and the blue wire together. Hopefully that makes a little bit of sense. Okay, like so. Do the best you can. Try to get these to wire net together. So you're going to have 2 of those like this. And then you're also going to have the other 2 wires. So hook these 2 black wires and the white wire together here. And I'll try to change the camera angle if I can to give you a better view of what this is supposed to look like. These smaller wire nuts are a little bit of a challenge, but try to get these wires hooked up together so that it looks like it's a parallel. This is a parallel circuit. So, all right, so you've got this wire and this, you got 2 wires together, hooked up together, and you have 2 wires hooked up together here. So you got this one and this one, the 2 left wires wired together, and the 2 right wires hooked together. The 2 right wires are hooked up to the control wire. The 2 left wires are hooked up to the common wire, to the return wire. And so this is considered a parallel circuit, okay? And when we read the resistance, so with a parallel resistance circuit, all of a sudden, okay, that's interesting. I got something not quite right here. Try it again. For some reason, I'm getting readings all over the board here, which isn't correct. What readings did you all get when you guys hooked those together that way?
13.3.
13.3. Thank you. That is the correct number.
I didn't change my common wires because it didn't matter.
Okay. Good. So that actually should work. So I got that one going through there and that one going through there. What's going on with mine? Trying to think. But anyway, so you should have 13 ohms there. So when you hook 2 wires together, when you hook 2 stations together in parallel, it will cut your ohms or your resistance in half. And what did I do wrong? Not quite sure.
Maybe check the connection on the blue wire. But
yeah, better.
Middle connection.
Okay. Are you guys getting 13 ohms ish? I hope. Hope you're doing a better job than I am.
I didn't move the common wires because it didn't seem like it would matter because they were still connected.
Okay. Oh, so you left this other common wire here?
Yeah, because it didn't seem like it would matter.
Right. I can pop that one back in and see. Shouldn't make a difference. Yeah, you're right. It should not make a difference. So, but I'll pop that back in and see what I get. But anyway, I don't want to. All right. So. Okay, got that one there. And that's even crazier yet. I'm not quite sure what happened there. Okay. Well, anyway, I don't want to. Okay, so that
The
would
only
be.
thing I see different is you've still got it connected to the common of the last two valves. I don't know if that would make a difference, but on mine, I don't have it connected the common to the last two, and mine's showing correctly.
Okay. Let's see.
Connected
Alright.
to all four. The common's connected still. I didn't touch the common. I just moved the valve wire over.
Moved it over. Okay. Well, let's see. That's this one here, and this one here. So I should just do that. All I should have to do is that, right? For my reading.
Could also be your diode that's underneath as well. Might have pulled one of the wires off.
Maybe so. Okay. I'll try station 2. Let's see if that makes any difference. Okay. I'll try station 2 instead and see if I get what reading I get there. Open sesame. Oop. Bouncing around still. There. Mine got all kind of silly. I may have done something kind of goofy to whatever I did on mine. Shoot. Okay. All right. So anywho, you should, whenever you, so as you guys know, oh, there we go. Oop, almost had it. There we go. All right. So when you hook two valves in series, when you hook two valves in parallel, it should cut the resistance in half. If you know, so in this case here, we had two valves at 27 ohms each, and so we're going to break it. It'll cut it in half to about 13 to 14 ohms. If we were to hook 3 valves in parallel, it would cut it to 1/3. So it would then cut your resistance down to about 9-ish or 10, between 9 or 10 ohms. So the only problem with hooking your solenoids in parallel, which is the way you're supposed to do it, if you're going to add another valve, is it cuts down the resistance and makes them a little bit more, I guess, apt to power spikes or a lightning strike or something to that effect, kind of a thing. Okay, so that's parallel. The next, what I'd like you to do next then is let's go ahead and hook them up in series so that you have an opportunity to see what that looks like. And I'll see if maybe if I can, hopefully I can do that successfully. And so what you'll do is you'll just hook your yellow wire like so. Your yellow wire will go into the first lead on station 2. It'll come back around and go ahead and then hook the these two middle wires here. Go ahead and hook these two together right there. So in this case here, hook these two together there. And you could be either using the yellow or the blue. It doesn't really, it wouldn't make any difference at this point. Okay, but it should look something like this. Hopefully I'm not confusing you all too badly with this right here. So, but it should look, whether you use the blue wires or the yellow, it should look something like this, where you've got the circuit coming in through here, it's coming down through here, it's going up through this one, down through this one, up through this one, then back around on the return wire back there. So whether you use the yellow or the blue shouldn't make any difference. And so you should have more of a this would be considered a series connection. And hopefully I'll get something. Thanks. I'm just gone silly with my stuff here. There we go. And so I'm getting about double. And so we've added, so when you hook something in series, you're going to add 27 ohms, and it's going to give you about 54, 55, 56 ohms. When you hook stations 1 and 2 together in series. Did any of you have any luck with that?
Okay.
Boy, mine's just gone kind of crazy. Hopefully you're having better luck with yours than I am with mine. There we go. Was anybody else able to get those kind of hooked up into parallel and into series? And again, it's going to be a 54.5. Great, Tim. So again, it's going to be a circuit coming up through here, coming out through there, coming into this one, coming out to that one, and then back in the white one. Great, Daniel. Good. So, and you could have used the blue into that. Hopefully, I'm going to try that. I'm going to just swap over here and go to blue. Should not make any difference. Should be able to go to the blue one. And I'm getting the same reading there. Whether I hooked up the blue or hooked up the yellow, didn't make any difference. Okay, so hope that makes a little bit of sense. All right, back up. Okay. So those are just a few of the things that you could kind of at least do when you're troubleshooting, is being able to isolate a particular valve or isolate, knowing the sequence of events as far as what to do, what wires to actually are bad. Is it a hot wire or a control wire, or is it a, excuse me, or is it the common wire or the return wire, those kinds of things. And then also, if you're getting some odd readings, is it based off of what's going on with, or do you have two valves hooked in series or a couple of valves hooked in parallel, those kinds of things. So, okay, so those are some of the things that I kind of wanted to go through as far as being able to kind of do a little troubleshooting, and maybe some things that we could do in the classroom as far as working with the students if you don't have a lot of controllers to work with there. So we've got a few minutes left, and I just kind of wanted to open it up as a forum for you all. Suggestions, comments, some of the things that we did here. What would you do differently, or with some things, or what are some things that we could do with the students as far as activities go, that kind of a thing. Anybody?
I just want to say, Brad, that was really good. This whole thing you've put together is really quite nice. Having the visual and something that's simple to ship is really, that's kind of the barrier that you reach when you're doing this hands-on kind of training stuff, is without sending a heavy controller and all that stuff to people. This is the simplistic way of getting them basically, trained on this troubleshooting stuff that is so crucial to technicians and stuff everywhere, and for the students that are going to, maybe be technicians or something one day.
So thanks, Greg.
It's really awesome.
So anyway, so like I said, my other goal was if you were going to ask like a test question or some homework questions, what kind of questions would you then ask some of the students, or what kind of things would you do with the students as far as this goes? What kind of activities, or an activity, or something that kind of popped out to you? Anybody?
I think some good questions could be situational, make them think, kind of like those worded questions that you always did in math class and stuff, right? So you say, all right, a homeowner calls you and says that none of their stations are working. What are the possible outcomes? And it could be water's not on. It could be the commons interrupted or been cut, things like that, to make them start thinking about situations that they're going to get calls on in the future. You know, again, if they're going to be in that field.
Good. So that would be, yes, very good. Also, and if you know the basics as far as, remember, power in, power out. Remember, it's controller, wire, and valve. And oftentimes you may skip the wire part and actually go straight to the valve and the controller, which can be a little bit easier for a person to do that. First, check, do everything you can that's easy to check with the controller itself. Go through there and find out, okay, what can we do with the controller? Well, we can find out, do we have power to the controller? Do we have power coming out of the different stations within that? And I don't know if I can, I'll see if I can pop that up real quick. And that would be, see if this camera is working. Ah, it is. Okay. So for example, what you could do then is when you're wanting to check power in, power out, and with this one here, it may be a matter of just checking, okay, I've got station 1 right here. Do I have 27 volts AC? No, I don't. Well, you may also then want to then turn, make sure you have the power turned on the controller itself and see if that makes a difference. So okay, and so we've got power to station 1 on, and so you would just go over here and check, and yes, I have 27 volts AC going out to station 1. And so that would at least tell you, then it's like, you bet, I've got power to here, and that means that if I hook up wires to it, we're going to have 27 volts running out to the solenoid. And so then that would be the next thing then, would be to check if I had a solenoid hooked up to that, would switch over to ohms, make sure that that's off. We have to make sure that the AC is off, so you would turn that system off. And then double check that and see what's going on with that. And we've got, right now we have it open because there's just nothing hooked up to that, but that would be the next thing that you would want to check then there, something like that. So anyhow, there's a number of different things that we can do with that. So, all right. Any other questions, comments from any of you all?
Brad, that's one of my favorite questions to ask, actually, is to give them a controller that's plugged into the, I have a bunch of controllers that I can just plug into the wall around the classroom. And I like to ask them that question of like, how much, voltage is your controller putting out? Because it forces them to remember they have to, activate the valve, and they also have to set their multimeter on the correct setting. And
Excellent.
so that kind of checks off a number of steps.
Wonderful. That's great. That's very good. Anything else? Anybody else? What else do you guys, that's great to do that. So those would be some very good things. So that would be one of the things to set up. If you've got controllers, be able to then do that. You can also then check, sometimes it may be a matter, is the, do you have, 110 volts into the transformer or whatever it might be, any of those kinds of things. So there's a number of different processes that can be
I've done a number of activities with voltage too, where you do the battery testing, because then they have to remember that's DC, and then they switch over to AC to test the wall socket or something. So
oh, good. And actually that would be a good sequence. Have them test a wall socket and then go in and then test the batteries. And if you know what the batteries are, then you would know if they switched back over to DC or not.
Yeah, don't do it the other way, because they may fry your multimeter.
So cool. Excellent. Oh, Dave, I guess I was looking just real quick before you blast off. I just wanted to go home. Let me see if I can get back to there. This was the acrylic box that I had built. This one here, and then if you wanted to, since it's acrylic, you can actually put different demarcation levels on here. And I usually use colored water. And then I asked the class, how many gallons do you think you can actually fit into that? And if you're looking at like a gallon jug, it looks like you can only fit about 4 in there, but that would be something else that you can have built and then get the weight of it and all of those things. So they can be quite helpful on that there too. So, but anyway, that was something we had talked about yesterday. So any other suggestions, comments, or just ideas that you guys have worked with? Anything else? So, okay. All right. I appreciate your patience today and actually being here from 4 to 5:30 for an hour and a half working with this. I really appreciate it. Again, if you've got any suggestions or anything else, let me know, and I'll be happy to help you with like a parts list, or if there's something else that you wanted to do with that, and kind of work with that. So great. Thank you, everybody.
Thank you, guys.
Thank you.
Thank you, Brad, for leading this awesome hands-on session virtually. We really appreciate you being able to teach us and do some hands-on despite us being virtual. So thank you so much. And thank you guys for tuning in to the Fundamentals of Electrical Troubleshooting. Our next webinar, Fundamentals of Two-Wire Systems, is tomorrow at noon Eastern. So again, thank you, Brad, and thank you to our sponsors, Rainbird, Hunter, Ewing, and Brightview. Thanks, guys.
Awesome. So thank you, everybody. Appreciate it.
Thank you, Brad.
Thanks, guys. Have a good one.